sound loudness, right? Okay, so here's the first problem. There are many problems that I just randomly collected some problems. So here's the first question. It says, first question is, right, how many decibel is hundredths of I naught? What is I naught? I naught is the threshold of hearing for human being, right, for us. And what's that value? Is 10 to the power negative 12 watts per meter square. So it's asking what's the decibel level for this, so you're now I is I naught divided by 100. That means it's 100 times less than our threshold of hearing, right? But some animals can hear that even that we cannot hear that, right? But some animals can hear that. For example, cat. Many cats can hear that sound actually. And what's the decibel level comparison? Loudness, right? That's what we measure the sound. So now just use straightforward formula. So 10 log I over I naught, that's the formula we have, right? Decibel level formula. And just put that I as 100 over 10. I naught over 10, that's it. So 10 log, this is I naught divided by 100, right? And in the you have 100. So I naught will cancel out. It's basically 10 log 1 over 100. And just do that calculation, right? That's the decibel level of this sound. So log of 1 over 100 is 1. So just use the calculator. Make sure you use 10 base log. It's negative 10. So 10 times, this will give you negative 2, right? And this is negative 20. What's the unit? Decibel. So cat can hear actually as low as negative 20 decibel. We can hear only 0 decibel, minimum sound level. But cats can hear actually negative 20 decibel, very quiet sound, right? So this is just a straightforward one, right? Any question? Okay, next. This is the next problem. So next one is this. Loudspeaker produces a sound level of 120 decibel at some distance, right? Distance is not given. What would be the loudness if there were 20 such identical speakers at the same distance, right? So here's the question. You have one speaker, right? Just one single speaker, right? And at some distance, we don't know the distance. You have, let's say initial, let's say beta 1, right? What's the what's the loudness in decibel scale produced by single speaker is 120 decibel. Now it says if you have 20 such speaker, similar, identical. If you have 20 identical speaker, right, 20 of them, right, at the same distance, what is the new decibel? That's the question. At the same distance, right? Same distance. Same distance R. What's the new decibel, right? So definitely it will not be 20 times this, because the loudness will not increase linearly, as we know, right? Definitely it won't be 20 times. But how do you find that? Just use the similar concept that I just showed you actually in the beginning. So you did, so first of all, if intensity will be, however, our plain intensity, if one speaker produces I, right, at some distance, due to 20, it will be 20 I, right? Because it does increase linearly. Our intensity does increase, intensity of power does increase linearly. If you have 20 speaker, the intensity will be 20 times I, but not this loudness that we hear. Okay, now just use the same formula. So beta 1 is 10 log I over I naught, right? And beta 2 is 10 log, now power has increased by 20, so 20 I over I naught. I naught is the threshold of hearing. So you just need now beta 2 minus beta 1. Just take the difference, right? And find beta 2. Beta 1 is given. So again, 10, so I'm going to do shortcut. So 10 log 20 I over I naught divided, using the log property, you know, I over I naught. So this will cancel out. Basically 10 log 20, right? So beta 2 is basically, beta 1 is 120 decibel is given, right? Plus 10 log 20. And that's gonna give you, so first of all, what is log 20? Log 20 is 1.3 and times 10 is, this is 13 decibel. So only 13 decibel increased plus one. So answer is 133 decibel will be the new sound level. So the decibel increase is only 13 decibel, right? Even if you increase the power by 20 times, right? The loudness will only increase by 13 decibel, right? Because it increases logarithmically. So that's the question. Okay. Any question?
Yeah, so why do you have to do beta 2 minus beta 1? Why can't you just solve for beta 2?
So how do you solve for beta 2 directly? Do you know the distance?
No.
Yeah, so if you know the distance, you could solve beta 2 directly by finding the power from here. First find the power, right? The speaker power. And if you know the distance, then you can directly use this formula, right, to find the beta 2. But in this problem, the distance is not given, so you cannot do that.
If the distance were given, how would you find that exactly?
Yeah, so if the distance is given, then you can do either this way, right, shortcut, or if the distance is not given, if the distance is given, then first you can find the power, right, the power wattage, right, of this speaker. Because why? Because you are given the decibel, right? So if suppose the same problem, right? Suppose the distance, let's put distance as 1 meter, let's say, just for example, right? If distance is given, say some distance, let's see. Okay, let's put some distance as 1 meter just for simplicity, right? Then you can solve the beta 2 directly without those equations, because first find the power, right? Because beta 1 is actually 10 log I over I naught, and then beta is 120, 10, right? Log I over, this is 10 to the power negative 12, right? That's threshold of hearing. And then this is 12 is log, so let's put I as I right now. And so first let's solve the intensity. And then once you find the intensity, since you know the distance, you can find the power. First of all, the log property, how would you get rid of the log? Because to solve the I, right, you have to get rid of this I, log. How would you get rid of this log? What's the log property?
You put it to the 10 to the power of that.
Yep, that's so it's called taking anti-log both sides, right? 10 to the power 12. Whatever you get, it becomes 10 to the power 12. Is now you're left with this. This is the log property in math. Okay, so your I is just what? This is 1 watts per meter square, right? And then, but I is what? Power divided by 4 pi r square. And then you can solve for power. Power is just 4 pi r square, right? 4 pi. R is 1 meter for simplicity, right? Just 4 pi, right? Put the actual watts. This is in watts. So once you find the power, then you can find the beta easily, beta 2. Because power of the speaker doesn't change, right? Now for beta 2, you have your I2 is what? I2 is 20 times speed, because you have 20 similar speaker, and 20 times 4 pi. That's your new power from 20 speakers. And then just do this, follow the same equation, 10 log I2, and you have to compare with the threshold of hearing. So 10 log I2 is this, 24 pi, right, divided by 10 to the power negative 12. That's it. And you will see, so find that out. Okay. Any question? Okay, now you can do the similar, right? So if the intensity of sound is increased by a factor of 5, right? The decibel reading of an instrument measuring the sound will increase by how many decibel? Basically, you're doing the same, exactly same. So you have beta 1 is some decibel, right? So it's basically asking the difference between two sound level. When you increase the sound by 5 times, increase the intensity. So it's basically asking beta 2 minus beta 1. So what is beta? Beta 1 is 10 log I over I naught. What is beta 2? Beta 2 now 10 log, you increase the intensity by 5 times. So 5I by I naught. And just take the difference, do some log algebra, right? And find that out. It's basically same, right? So these are all similar. So let's do one more.
Just for a second.
Which one?
To number 3.
This one?
Yeah, I'm good. Thank you.
Yeah, so number 4, number 5, similar. So let me do one more. A rock band playing an outdoor concert produces a sound at 120 decibel, right? The rock concert usually produce actually that much sound level. That's the actual number actually. Rock band produces just like a jet engine actually, okay, single jet engine. 120 decibel sound is very intense sound actually. At what distance? Now you are given the distance, 5-meter distance away from their single working loudspeaker. What is the sound intensity level, however, at 35 meters away? So here's the thing. Now you have only single speaker, right? And it says at R1 is how much distance? 5-meter distance, right? This is the observation point. Your loudness is 120 decibel at 5-meter distance. Now it's asking, the speaker is the same, right? Now at further distance, 35 meters away, what's the loudness? Clearly loudness will decrease, we know. So now your distance is 35 meters now, right? What will be the new loudness? So that's the question. So then you just do the same thing that I just showed you. So first find the power, right? And power will not change, right? Because you use the same speaker. The speaker power will not change. So from this first data, since distance is given, first you find the power, right? So beta 1 is 10 log I over I naught. So this is 120 decibel, 10 log I over I naught, right? So again, it's 10 to the power 12, right? Is I over I naught is 10 to the power negative 12. So I is just 1 again, 1 watts per meter square. Then you can find the power of the speaker, because I is what? I is power divided by 4 pi R square, R1 square, right? This is I1. So power is now 4 pi R1 square, because I1 is just 1. So find that out. This is the speaker power. 4 pi, so R is 5 meter initially, right? So the power is 314 watts. That is constant, right? The power of the speaker doesn't change. Now it's asking what's the loudness at 35 meter distance. Now you have to calculate beta 2, right? To find the beta 2, first you need I2, the new intensity, right? Is power will remain same, but distance is different, so R2 squared. So it's 314 divided by 4 pi 35 square, right? So I2 is now 314 divided by 4 pi, right? But distance is 35 now. Okay, now it's going to be, the intensity will be 0.0204, right? Watts per meter square. Now, what is the new loudness? So new loudness will be now back to same formula, 10 log new intensity divided by threshold is 10 log I2 is 0.0204 divided by 10 to the power negative 12. And your beta 2 is, what is the 0.02, so log, 10 base log 0.0204 divided by 10 to the power negative 12. Okay, so that's going to give me 10.3. 10.3 times 10 is 103 decibel, right? Remember, beta 1 was 120 decibel, and that was at 5-meter distance, right? Obviously, it will be intense, right? Loudness will be intense actually at low distance. So at 5-meter, it was 120 decibel, but if you go farther away, 35-meter distance away, the loudness has decreased by 17 decibel. All right, guys, any question? Problems now based on this. So here's the first problem. Just to get started, we're gonna do the simple one. So this is the first problem I'll be showing you. Okay. So here's the first question. This is the end of the chapter problem from my lecture slide. Let's see first. So here's the question. It says, a friend of yours is loudly singing a single note at 400 hertz, right? Is singing at 400 hertz and approaching towards you, okay? It's while driving towards you at 25 meters per second on a day when the speed of sound is 3, it says to use 340 as the speed of sound. What frequency do you hear? You are at rest, right? And what frequency does your friend hear if you suddenly start singing at 400 hertz, right? And what frequency does your friend hear if you suddenly start singing at 400 hertz and moving towards your friend with 10 meters per second? So these are the questions, you know. So let's use the Doppler formula, right? So let me go back and try to solve some problems based on that. So here's the so Doppler effect problems. So that particular problem for my lecture slide, it says, so here's the question. So this, let's say you don't need to draw all the pictures. So you're a listener right now, right? Your friend is driving towards you. So your friend is the source, right? Your friend is driving towards you at what velocity? Velocity of what? Velocity of 25 meters per second. So initially you are at rest, right? So what frequency, and your friend is emitting 400 hertz as the original frequency. This is f of s. F of s is the original. So what frequency, what apparent frequency, you have to say apparent frequency, right? Do you hear? And that's pretty easy, right? So the apparent frequency that you will hear is based on this formula, f of s, right? That's the original frequency. This is the apparent frequency. So now you have to adjust these formulas. So remember, let me first write down the formula. This is the formula you have, right? Listener in the numerator and source velocity in the denominator. This is the speed of sound, which is given. Okay, now this is 400 hertz. That's the original frequency. The speed of sound is 340. That's what it says to use. And the listener is now approaching, no, listener is you. You are at rest, so 0, right? So listener is 0 because you are the listener. So now source is moving towards you. So do you use plus sign or minus sign in the denominator? The source, which is your friend, right, is moving towards you, right? So and we know when source is moving towards you, the apparent frequency has to increase. We know from common sense, right? If source is moving towards you, the apparent frequency will increase. So to match that, so what actually sign do you use? Plus sign or negative sign? So tell me, do you use plus sign or negative sign?
Negative sign.
Negative, yep. Why? Because it's in the denominator, right? And making minimum in the denominator makes the whole thing maximum, I mean increase, right? Because we know that the apparent frequency will increase. We know that from common sense because it's approaching. Okay, that's it. That's it. So it's 340 minus, and it's approaching at 525 meters per second. So that's your answer. So do that calculations. So 400 times 340 divided by 315, right? Okay, so it's 432 hertz. So you'll hear that sound as 432. Even if the original frequency is 400, you will hear that frequency, right, as 432. The apparent frequency increases, right, as expected. That's part A. So part B. Now it says, part B says, now what frequency does your friend hear if you suddenly start singing? Now you're the source, right? Now second, it's different for different problems. Situation is different for different problems, right? Now this is the scenario. Now you still at rest, but now you're singing sound at 400 hertz, right? And your friend is still approaching towards you. Your friend is now listener. Your friend is listener, okay? And is approaching towards you at 25 meters per second, right? Now you are a source because you are singing, and your friend is listener, okay? Situation has changed. Now what apparent frequency does your friend hear, right? Apparent frequency heard by your friend, right, is now same thing. So just match plus and do play with that formula, right? So now from the given equation, so your listener, right, listener is approaching towards, so V plus VL, right, because it's approaching towards, and your source is at rest, your source now. That's it. That's your equation. So this is still because you're singing at 400 hertz. So this is the speed of sound. So V is, don't get confused, it's the speed of sound in the given medium, in the air, right? It will be given to you. Plus approaches is still approaching at 25 and 340. That's it. So that's the frequency that your friend will hear, 400 and 365 divided by 340. So 429, slightly different, but it still increase. Okay, now that's it, right? That's simple. And now next scenario, part C, is now like this. Now both are moving. You, right, still singing at 400 hertz, but you are now moving towards your friend at 10 meters per second. You are still source. You're still source. Your friend is approaching towards you at 25 meters per second, right? Still listener. Now, what frequency does your friend hear? That's what it says, right? Who is the listener? So what frequency does your friend hear, right? Your friend is still a listener. Okay, now you have relative motion, both relative motion, right? Both are moving towards each other. So now again match that. So F of S. So listener is moving towards, so you need plus sign. And source is also moving towards, right? So you need to minimize it here. So that's it. So this is again 400 hertz, 340 plus The listener is your friend, 25. However, you're moving with 10 meters per second. Okay, so that's the apparent frequency that your friend will hear. Okay, it's going to be 442. And apparent frequency has increased, right, by 42 hertz. Still. Okay, so that's how you just need to play with this formula, main formula. Just need to understand which one plus and minus use, you know. Any question? Any question? Okay, let's do little tricky one. So that's number 2 is similar. Number 3, let's read number 3. Number 3 says a police car with its 400 horse siren is moving away from the warehouse, right, at a speed of 40 meters per second. What frequency does the driver of the police car hear as reflected wave from the warehouse? I mean, you can call it echo, right? So it's just asking, what echo frequency will the driver of the police car, right, hear from the warehouse? Warehouse is a kind of reflector, right? It's the wall of the warehouse, act as a reflector of the sound. Assuming that ear is still and the speed of sound in ear is that. So here's the hint, main idea. The wave fronts, right, the wave fronts are reflected from the wall of the warehouse at the same rate that they are incident on it. So that's the main idea. Okay, so let me try to explain what that means. Okay, now next problem, little tricky. So this is number 3 from my lecture slide. Okay. So question is, so this is the warehouse wall, let's say. I'm just drawing this. And this is the police car, right? It's moving away. Police car is moving away, but it's making sound which gets reflected off the, right, like this, and it's asking what echo frequency, right, will be heard by the police. Right? This is the warehouse wall. Okay, first we have to, now the main idea is the wall will reflect the sound wave at the same rate that it incidents on it. Okay, that's the main idea, the hint. The wall will reflects this wave at the same rate. Rate means frequency, as it is incident on it. That means, so what frequency does the wall hear? So let's say wall is listener now. In first case, wall is, you can break into 2 parts. Wall is now listener, because we want to find out what frequency will be detected by the wall, right? And it will be reflected off by at the same rate. That's how the wave behave. Okay. Now first case is wall is listener, and the car is source. So we want to find what frequency will be incident on the wall, right? So this frequency, right, is now based on the, so V is speed of sound. It says to use 343, right? So V, now with listener first, right? So listener is wall is at rest. So V, and the car, police car is the source, right? Car is the source, but it's moving away. So away means you need plus sign. Police car, right? Source is the car here. Okay, now let's first find that out. The original frequency is what's the original frequency? 400 hertz siren. So 400 hertz. And 343 divided by 343 plus, what's the car speed of the car? Speed of the car is 40 meters per second. Okay, so this is the frequency that will be incident on the wall, warehouse. Okay, so first find that out. So 400 into 343 divided by 383, right? And that's going to be 358 hours. And again, now I'm going to use this idea, this hint here. See, the wall reflects the wave at the same rate, at the same frequency as it is incident on it, right? That's what I gave you as a hint, right? So this 350 hertz is the frequency of the sound, which will be incident, which hits the wall. Now, second part. Now, wall is source, right? Because we want to now do one more Doppler shift, double Doppler shift. Because now wall, now for the police car, right, which is moving away. Now, wall works as a source of sound because it's reflecting the sound, right? But the listener is moving away now, right? Now, in second case, now you have to switch the role. So now police in the car is listener. And the wall, the warehouse wall is source because it's reflecting off the surface, right? It's reflecting the wave. So wall is source and police is the listener. Now, finally, second, it's called double Doppler shift. Now, what will be the frequency? Now, source emitting that much frequency. Wall is the source of sound which is emitting F1 hertz, F prime hertz, which is 350. So you have to now use the original sound wave as F prime because that's right. That works as the original frequency now because wall is reflecting right at that rate with that much original frequency. So V now police is moving away, right? Police is listener moving away. So VL divided by wall is at rest. So VS is 0. And that's your final answer. So this is now 358. That's the little trick. That's all. So listener is, car is the listener, which is moving away at 40 meters per second, 343. That's it. That's the final Doppler shift. So problem like this, echo problem, you have to do double Doppler shift, right? One, listen by the wall, and again, when it reflects back, you will have one more Doppler shift. So 358 times 343 minus this, right? And divided by 343. Okay, 316 hertz in 360. So that's the frequency heard by the driver in a police car. Finally, so you can clearly see right what's the original, very original frequency, 400 hertz. That's the siren frequency, right? But the driver in that police car will hear only 316, huge shift, right? 316 hertz, and because the main reason is it's moving away from the wall, and there is a double Doppler shift. So that's how you, and this is called echo actually. Echo frequency. So whenever you solve echo, make sure you have to do double shift, double Doppler shift. Here's the next question. So this is a question on the radar guns. So police use radar gun, to track or to measure the speed of, a speeding car, incoming car. And radar guns are in their most simple form, basic form. They are just a signal transmitters and receivers, and which use Doppler's effect, so they first send out the signal and then receive the signal, and they just based on the shift in the frequency, it can calculate the speed of the car. That's how it works. So it says the radar gun, right? uses 30 kilohertz as a signal. It sent out 30 kilohertz signal, and the radar detects a frequency difference of 3 kilohertz. So since the car is incoming, right? So it detects the echo frequency, right, reflected off the incoming car as 33 kilohertz, right? 33 kilohertz, because 3 kilohertz increase in the signal when it reflects back off the incoming car. So then based on this information, it's asking what is the speed reading on the radar gun. And so these are ultrasonic. So ultrasonic wave is also sound wave, so its speed is 343 meters per second. So the main idea is, first, here's the hint: the wave fronts are reflected from the car, right? Car at the same rate that they are incident on it. So suppose here's the radar gun, right? This is the radar gun is the police, right? Is holding the radar gun. It is at rest and is sending the signal, and it's reflected off the car. It's reflected off the car, but we know it will be reflected at the same rate that it is incident on it. So that's why first let's find out the frequency of the echo, okay, reflected off the car. And that's really easy because the car is incoming, right? We don't know the velocity of the car. Let's say v of c, let's call v of c, and then f, this the echo frequency, right, is the frequency reflected off the car will be from Doppler's formula is Vs, V plus plus or minus the listener velocity. So listener is car right now, right? So it's incoming, so VL, right? VL means V car, right? In the first case, car is the listener, and the radar gun is the source, divided by, since radar gun is at rest, which is emitting the frequency, right? So its velocity is 0. So that's the first frequency, right? First we're going to solve algebraically. Now next, right, but there will be second Doppler shift, since now you have to consider in second case as the incoming car as the source, right? Source which is emitting this echo frequency, emitting this echo, right, of frequency f prime, this exactly this frequency, and radar gun, right, radar gun as the listener. Why? Because it is detecting now. In second case, next Doppler shift, you have to consider the car as a source of sound, which is emitting echo of frequency f prime, which is this, and radar gun as a listener. Now the frequency detected by the radar gun, which we know 33 kilohertz, right? This is the frequency detected by the gun, radar gun, right? Which we know is 33 kilohertz, because it says 3 kilohertz shift. Now what will be the next Doppler shift? Now you have to consider f prime as the original frequency, because the car is actually emitting this as its original frequency. Now car is the source, right, and radar gun is listener. So listener is 0, right? Listener is at rest, and V, since the car is source, which is going towards the radar gun. So towards means negative, you need negative. So source, V of source is V of car, right? And but f prime we already know. Let's say equation number 1. So f prime is the original frequency fs, and v plus v car divided by v times, you have this second term, v divided by v minus vc, right? And that's it. So that's going to be your main formula, and this will cancel out, and then this ff source is 30,000, right? This is the main frequency of the source, original frequency 30 kilohertz, 30,000, right? And then you have this v is the 343, right, plus the v of car, which we are going to solve, and again 343 minus VC, and this is 33,000. You have to convert into the hertz. 30,000, 343 plus VC divided by 343 minus VC, and then you just now solve this algebra, right? Just solve this algebra, right, somehow, and then the car velocity will be about 16.3 meters per second, which is about 30 miles per hour. Okay, so that's how you solve this Doppler effect problem with the radar gun. Okay, so if suppose two speakers are just separated along the X line, right? And sometimes the two speakers may separate like this. Sometimes the two speakers may separate like this. So then the question is, is this a loud spot or quiet spot, and then so on, right? So let's get started with the simple one. Here's the first question, right? So I'm just gonna solve some first question. So here's the same question. So it's just asking this particular question. So there are two speakers, identical speakers, right? Driven at exactly same frequency, 2.2 kilohertz, right? Two speakers they are separated by 1.25 meters. Produce sound coherently, means exactly in phase. Two speakers must produce in phase signal, if right initially. And the speed of sound is given. It says to use 341. What will the listeners hear at point A and point B? So that's the question. And it says A is a midpoint between two speakers, and proved by numerical calculations. So now suppose the listener first stands at A, right, and then go to B. So what do they hear? Will the listeners hear at point A and B quiet sound or loud sound? So so at A, right? So A it says midpoint, right? What you need is the path difference. Let's say L1, right, is the path. L1 is the point A from the first source, right? And then you also need one. You also need, this is midpoint actually. So somehow this got shifted, right? But this speaker is, this point is at same distance. This speaker somehow actually, when I printed, it got shifted. But L1 and L2 are same. So then the two sound wave reaching here, right, like this, will meet like what? What will be the path difference? That's the path difference, right? You just need the magnitude. 0, right? So then take the ratio, because we have to check, eventually you have to check this ratio, right? And what is lambda? So no matter what lambda is, right, it doesn't matter. It's always 0, right? 0. So that means it's constructive interference, right? Because the two sound waves reaching here will always have chance to meet in phase. Because why? Because this ratio is 0, equal path difference, because of equal path difference. So it's a loud sound. You will hear a loud sound. If you stand here, you will hear a loud sound due to the constructive interference. Okay, it's a loud sound spot, right? So you don't need to calculate lambda, because no matter what lambda, it will be always constructive, because it will be always 0. Okay, at B. So at B, first you have to, so at now if you reach here, if you stand at point B, right? So then what is your L1? This is your L1, right? This is your L1 and this is your L2. L1 and L2 are just the distances, right? From the given sources. So what is L1? What would be L1 at B? So from the given variable, given information, how do you find L1?
You have to find delta L first. Or to find L1, it'd just be the full length minus B.
Yeah. So it's going to be just the full length minus this, right? Yeah, the speaker is right here, so don't get confused actually. The speaker is right here. Speaker is right here. Okay, so L1 is, yeah, full length, which is 1.25, right? Minus this, 0.431. 1.25 minus 0.431. And it's going to be 0.819 meters, right? And what is your L2? L2 is just this, right? And L2 is given to you, 0.431. So path difference is just basically that. So path difference is just 0.819 minus 0.431. Just 0.388 meters, right? So that's your path difference, right? Now, what's the next information you need? The next information you need is lambda. You need lambda. Lambda is V over F, right? And V is now this is a sound wave. We're talking about the sound wave, right? And velocity of sound, it says to use 341, and the frequency is 2.2 kilohertz, but it must be in hertz. So 341 divided by 2200, 2.2 kilohertz is 20. So, and check that ratio, 341 divided by 2200. That's going to give you 0.155, right? This also in meter. Okay, now finally check this ratio, because eventually that's what you need to do, right? The path length divided by the wavelength ratio is going to be what? And based on that ratio, you need to figure out whether it's going to be constructive interference or destructive interference divided by 0.155. So it's going to be 2.5, right? Okay, so this ratio came out 2.5, right? So then is it a quiet spot or loud spot then?
It's quiet.
Yeah, it's a quiet spot, right? Why? Because this is the criteria for destructive interference, because the path length difference is 2.5 times lambda, right? That simply means the path length is just 2.5 times lambda, and this is for destructive. The two sound waves reaching here will meet out of phase. So it's a destructive interference. No sound. So that means ideally no sound. Okay, so even if both speakers are on, so ideally, right, in principle, if you stand at this point, you will hear no sound or very little sound. So that's how you figure out. So you're going to need these two information, this and this. Just check the ratio. Okay, now we can do one more like this again, but these two speakers so some person is right here, standing here, this laterally shifted, right? So here's the question. So two speakers are separated by 3 meters, right? And Sam is standing at 4 meters from the second speaker, let's say, right? And these two speakers are driving at 170 hertz, right, frequency. And the speed of sound, it says use the speed of sound at that particular temperature, use 340, right? It will be different for different problems, slightly. Ideally, it's 343. And here's the question. Is this a loud spot or quiet spot, right? Does Sam hear a loud sound or quiet sound? And exactly, you have to do exactly same, right? And then the second question is, what is the next frequency for which Sam will hear an opposite type of interference as in part A? So first you need to figure out part A, is this a quiet spot or loud spot, right? You first need to, and how do you do? So this is your L1, right? Let's say this is speaker number 1. Let's say this is speaker number 2, let's say, right? So this is your first length, right? And this is your second length, which is just the diagonal distance. And this is 3, 4, 5, right? 3, 4, 5. So that's it. So your path length is simply L2 minus L1. You just need the magnitude, right? So 1 meter. And lambda, again, lambda is V over frequency. If you are not directly given the lambda, you can find that out. And it's going to be 340 divided by 170. 340 divided by 170. So this is what, 2, right? And delta L, now you have to check this ratio. Delta L over lambda is 1 divided by 2 is half. So again, this is destructive interference, right? This is a quiet spot. But even if both speakers are on, the Sam will not hear any sound or very little sound because of cancellation, right? So that's part A, that's easy. Now the next part is, it says, what is the next frequency? So now you slowly increase the frequency, right? You can tune the frequency, right? Now it says, now you slowly increase the frequency until you hear opposite type of interference as in part A. So you hear quiet sound, right? Now you want to hear a loud sound, right? Because you in part A, this is destructive. And now you want a constructive interference. Sam is still there, right? Sam is still actually standing there. So you just change the frequency. You slowly increase the frequency, right? Until you hear the loud sound. Loud means we need constructive interference based on the question, right? Okay. And tell me the idea. So now at what next frequency? So you start off with 170 hertz, you hear, the Sam will hear quiet sound. Now it says to slowly increase the frequency until Sam hears, a loud sound, constructive interference. So how do you do that? Give me some idea.
If you double the frequency, then the lambda will be 1, and the ratio of delta L over lambda will also be 1. Yep,
because the positions are same, right? Nothing is has changed. The position of Sam is same. The speakers are same. You are allowed to change only frequency. So then you have to find the new lambda, right? And we know what's the next. Well, the next possibility is 1, right? The next possible ratio is 1. Then you hear actually a loud sound, constructive interference. Then you find because path difference has not changed, it's same, right? And you find the new lambda first. New lambda will be delta L over 1, right? So delta L has not changed, it's same, 1 over 1, yep. So 1 meters, right? And then you convert back to frequency, that's it. So your new frequency is V is same, right? So V is 3, what does it say to use? 340. 340 divided by lambda is 1. So 340 hertz, right? You have to double the frequency, yep. So the main idea is this. This is the main idea, right? You have to change that ratio, this ratio, to the next ratio so that you get constructive interference, and then find the new lambda and then convert lambda into frequency. Here's the next question on interference. So it says two loudspeakers in room emit 281 hertz sound waves along the x-axis, and it's asking what is the smallest distance between the speakers for which the interference of sound wave is destructive, so quiet sound. So let me first draw the picture. So you have these two speakers are lying along the same direction. So these are the two speakers, right? Let's say, right, just rough picture. And so it's asking what is the minimum distance, right? What is the smallest distance between these two speakers, so that so let's say this is the listener standing, say here, right? Will hear destructive interference or no sound, right? So our condition. So let's see what is the condition for destructive interference. So destructive interference condition is delta L, right, which is the path difference between these two sound waves must be what? Must be odd half, right? So m plus 1/2 lambda. So odd half multiple of lambda. That's the condition for destructive interference. So for the shortest distance, m is equal to 0 for shortest distance. So delta L has to be what? 1/2 of lambda, right? But what is the path difference? So path difference is this. So from the first speaker, let's say this is L1, right? From the second speaker, this is L2, right? So path difference is basically x, right? Basically path difference, which is delta L is L1 minus L2, right? L1 minus L2 is basically x, which is the separation between the two speakers. So 1/2 lambda, and then so you can find lambda from V over F. So speed of sound in air, if it doesn't say anything, just take 343 meters per second, and the frequency of the sound used by these both speakers are 681. That's given. So that's gonna get you 0.504. So 0.504 meters, and then that's your answer. So then the smallest distance is just half the wavelength, right? And then just divide by 2, gives you 0.252 meters, right? Or in centimeters, it's 25.2 centimeters. So that's it. So the smallest distance you can have is 25.2 centimeters, so that the observer somewhere here, right, anywhere here, will hear a destructive sound, no sound, right? And it definitely depends on the frequency, what frequency of sound it is emitting. Now next, second part of this question is, what is the next distance for which the interference of sound waves is now constructive interference? Now we want the constructive interference, right? And what's the condition for constructive interference? Constructive interference condition is delta x, delta L is m lambda, right? But m cannot be 0 here, because otherwise the separation between two speakers will be 0. Definitely we have already found the smallest distance between two speakers here. So m will be 1. The next possible interference will be gives you m is equal to 1. Delta L is x is lambda, right? And again, lambda is what? V over F, and this is 343 divided by the frequency is frequency 681. So 681. So that's gonna give you 0.504 meters, or in centimeter 0.504. So 50.4 centimeter is the next distance separation between two speakers, right? So then you will hear a loud sound along the by the this listener here. So here's the next question. It says, so again, you have two sources of sound, emitting sound at same frequency in phase coherently, and it's asking what are the three lowest frequencies in the audible range, at which fully destructive interference will occur at the position of the observer as shown in the diagram. It says ignore the decrease in intensity that occurs with the distance from the source. The speed of sound is 341 meters per second. So it's basically asking what's the first three lowest frequencies in the audible range, at which you get this observer will get destructive interference, no sound. So you have to figure out the first three frequencies, such frequencies, but it should be in audible range. So what is the audible range? So audible range is audible range, right, for human brain is from 20 hertz to 20 kilohertz, 20,000 hertz, right? So make sure when you solve for the frequency, it should be within this range. Okay, so we are finding the condition for destructive fully destructive interference again. So this is the condition, right? So condition for destructive interference is path difference, right? Has to be m plus 1/2 times lambda, right? So but path difference is what? Path difference is this minus that. So 17 minus path difference is longer path minus the shorter path, right? So 41.6 minus 17.1. So we're gonna find the first possible. So starting from with 0, right? So lambda, right? 1/2 lambda. So lambda 1 is then the first possible is given by 2 times delta L, right? And if you do that, so it's going to give you 49 meters. Okay, and what's the frequency associated with this? So frequency is just the speed of sound, which is constant, divided by lambda 1. So frequency of sound, it says to use 341.49. So that's going to give you 7 hertz. But the problem is it's not audible. You cannot hear this frequency 7 hertz because it wants you to find the audio in audible range. So let's keep solving this actually. So the next possible is m is 1 and 1/2 lambda, which is 3/2 lambda, right? And then your lambda 2, which is the next possible lambda, is 2 times delta L over 3. So 2 times delta L is the path difference, right? Which is always constant for the given situation, is 24.5 divided by 3. That's going to give you 16.3 meter. And then the frequency associated with this is then V over lambda 2. So 340, it says to use 341 divided by lambda 16.3. So that's going to give you 21 hertz. So you can hear it. So that's your first frequency, right? So the next is, you just keep doing that. Delta L next is what? 5/2 lambda. So lambda 3, right, is 2/5 of delta L, path difference. So 2 times 24.5 divided by 5 is lambda 3 is going to be 2 point, right? So it's going to be 9.8 meters. And then frequency associated with this is V over lambda 3. So 341 divided by 9.8 is going to give you 35 hertz. And one more frequency because it wants you to find the first three. So the next is delta L is now what? 5/7/2, right? It goes with odd half multiple of lambda. So lambda, next lambda 4 is twice times delta L over 7. So 2 times delta L is always constant, 25.5 divided by 7 is going to give you the next, right, is going to give you so this is 2 times 24.5 divided by 7 is 7, right, meters, and then frequency is 341 divided by 7. So 341 divided by 7 is 49 hertz. Okay, so so these are the answer. This first, second, third. These are the first three frequencies in audible range for which the observer will hear no sound, destructive interference.